can't see that because my camera looks like there's a solar flare coming through my window, but there's some bloke out there who's like spraying the grass. Anyway, the next one we're going to look at is the hyperbola. So again, the theme of the next week or so is just going to be looking at different types of graphs and performing the exact same transformations. So moving them left and right, moving them up and down, but it's just a matter of identifying what these graphs look like and like what they are. So hyperbola is our newest one. It looks like y equals something over x. So your most common one is just going to be 1 over x. So if you look in the top left-hand corner, that's what our graph looks like, and I'll explain why it looks like that in a second. But is what it looks like. And I guess if you just see too little, they kind of look like, oh, not really. You can't really call them parabolas, I don't know, little curves. Then you just look at a parabola. Sorry, a hyperbola. Now, it tells you how to pronounce it here. I think that's the way people saying hyperbola. It's not called that, it's a hyperbola, but whatever. So if you're just looking at standard 1 over x, then you're in these two quadrants. And the reason is because when I put a positive value into here, into my x, then the output, which is my y value, will have to be positive. If I put a negative into there, then my output has to be negative. So that's why I'm in the positive x and the positive y, and the negative x and negative y. That's why I'm kind of residing in these two, and it's impossible to have something in here. And the converse can be said for this one, because I'm starting with a negative, it's going to be like the opposite, like either x is positive or y is positive, like it can't be both. For instance, if I put -1 into there, the output is going to be 1. If I put +1 into here, the output's going to be -1. So that's why I'm kind of in positive y, negative x, and positive x, negative y. So that's kind of why that makes sense. And I guess that's kind of it. The only difference the graph makes when you change the k value, it just, again, that's like a scalar. So you could rewrite this as y equals k times 1 on x, and you could call this the gradient, I suppose. It just means that the line's going to go up a little bit steeper, so it might just like go really, I don't know, like this or something, if that makes any sense, like it's a little bit steeper. But other than that, you can't really tell the difference between 3 on x and 100 on x, really. I mean, if you go up the top here, I'm just going to increase it. It looks like it's separating, but really what it's doing is just getting heaps steep. So it kind of looks like moving away, but yeah, it's just getting steeper. Okay, so that's what the graph looks like. So the second you see two distinct little lines here, you'll call it a hyperbola. And then I just wanted to go over this. I'm not going to write all these because some of them are pretty intuitive, I guess. It basically says this has two separate branches in different quadrants. Yeah. If k is positive, then the graph is in the first and third quadrants. So that's what I was saying here. For the positive case, it's in these two. The negative case, it's in the second. So this is 1, 2, 3, 4. The second and the fourth quadrant. It says the graphs have axes of symmetries, y equals x and y equals minus x. Y equals x looks like this. So that's y equals x. Y equals minus x looks like that. So that's the axis of symmetries. That's all that's saying. Rotational symmetry of 180 degrees. That just means if I grab this and I rotate it 180 degrees, so I go around the whole way, it'll look the same. That's all that means. It was the same with the cubic. Remember how I rotated that and I ended up with a cubic again? That's all that's saying. The higher the value of k, the further it is from the x and y axes. So that's what we're looking at in the top left corner. It looks like it's going further away, which it is, but another way of describing that is just it's getting steeper. Okay, this is the important thing, and there's a way of writing this. It's as x becomes very large, y gets closer to 0. So what that means is, so we're looking at this one, as x gets large, so in other words, as we move along this direction, in the x direction, as it gets bigger, my y value, which is how high it is, approaches 0. So in other words, the graph gets closer and closer towards 0. So it just kind of goes that way. Another way of writing that, and I guess I want people to take this out, it's as x approaches, or becomes very large, approaches infinity, y approaches 0. So in other words, as I make x really, really big, y gets closer and closer to 0. And you can see that in the graph up top here. As I move along the x-axis, the graph gets closer and closer to y equals 0, which is the x-axis. But never touches it. And I'll explain why it never touches it in a sec as well. And the converse can be said, so as x becomes closer to 0, so as it's kind of like up and down, as we're approaching 0, so this way, let me just draw it, as x approaches 0, so as we're going towards this, y is getting massive, so this is just going up and up and up and up, and up, but it kind of approaches x equals 0. So another way of writing that is, as x approaches 0, y approaches infinity. And yes, that arrow means approaches, and there's a lot of different arrows that mean different things, like we've used this, we've used that now, there's actually that, there's this, there's so many different arrows. Anyway, now the graph gets close to the x and y axes but never crosses them, so that's what I said just then. These are called asymptotes. So an asymptote is just the line on your graph that a line on your, what do you call it, on my Cartesian plane that the graph will never touch. So in other words, the graph is never going to touch here and it's never going to touch here. Now you call those two asymptotes, and normally to denote an asymptote, you'll just draw a dotted line to say that, okay, it's never going to touch here. But since my dotted line is on top of the axis lines, you're not going to draw them. But when we start moving these things left and right, we are going to draw them. Okay, so that's everything to do with the hyperbola. I'm going to leave that one in the top left so that you can get an idea of what the normal one looks like. I like comparing it to the original. Right, I want to graph these two things. So let's call this A, let's call this B. So the first one, boom, 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 boom. Y, X, Y, X. Okay, now, y equals 2x. I know that my hyperbola looks like this, and like this. And I can draw arrows on the end of those. And the 2 just makes it look a little bit steeper. Cool, I guess. This next one, minus, that just means I'm sitting in different quadrants. So I'm going to draw it like, maybe I'll draw it a little bit steeper. So maybe a bit further away, maybe. I don't know. Now, I guess where I'm going to go with this is there's not really any way of distinguishing the two graphs. Like they kind of look identical. Like how do I know that this one on the left is 2 on x when it could be like 100 on x? There's no real way of determining the scale. So what you'll generally do is just chuck some random point, so maybe a point like here, on the graph that kind of tells you where it touches, because look, like this could be a million, or this could be 0.1, I don't know, there's no scale. So you just chuck a random point on here. You kind of want them to be whole numbers, so you just kind of think about what could I put in here that's going to make this a whole number? Well, if I made x equal 2, then y is going to equal 1. So I could have the point 2, 1 on there, and that's perfectly fine, as long as there's 1 point on there. So again, with B, maybe I want to chuck a point here. Let's find an x value. So, okay, what can I use to make this a whole number? Well, I could put a 3 there. If I put a 3 there, this is going to equal minus 1. So that's the point 3 minus 1. Look, it does not matter where your point is. But know that it's also symmetrical too. So if I want to find this point, what can I put in there? Well, I could put minus 3, and this is going to equal 1. So this is the point minus 3, 1. So it's kind of like the same as this. So you can do that, you can put 2 points, don't really care, as long as there's 1 point to kind of distinguish the scale. That's all I'm asking. And that's really as far as we go with hyperbolas. Just kidding, we're going to move them up, down, left, and right. Now, this is where we start moving our asymptotes. So just think of, like, this is my normal graph, k on x, this plus c on the end, that just moves it up or down. So that just moves it up or down, and we call that a vertical translation. So vertical, up and down, translation means moving. And remember when we had our y equals, it was x minus c squared or something like that? Remember how it was like I was replacing the x with x minus c? It's the same thing here. I'm replacing my x with x minus, now they use r, I'm going to change that to a c. Change that to a c. That's translated c units to the right. Okay. So again, it's the opposite. So the minus c moves to the right, even though that's in the positive direction. So it's a little bit confusing in that regard, but it's the same thing. I just think of it like if the plus c is on the end, kind of like a constant that's on the very side, that makes it go up and down. If it's inside, like if it's right next to the x, see how here it's not right next to the x? Right here where it is 100% next to the x, that's a horizontal translation, which just means I move it left and right. Horizontal translation. I didn't want this video to be too long. Damn it, it's 10 minutes already. But these are the only two examples. Alright, so again, I'll just draw my original, and then then change it. Let's do A, B next to each other again. Now, the easiest way to draw hyperbolas when you're moving them, I think, this is just personal preference, but obviously you can do whatever you want, as long as it's correct, is this. That bloke outside's not watching me. He's not. Okay, so I know that there are asymptotes here and here, which means the graph doesn't touch there. So what I'm going to do is I'm going to move that. Now I'm going to move these, so you can think of it like, I'll draw them in red. You can think of it like this. I'm going to move those asymptotes up 1. So this tells me I go up 1. So I'm going to grab this and this. I'm going to move it up 1, and then my new asymptotes. Now obviously I'm going to draw this one because it is the x-axis, the y-axis. Okay, and I should probably make this dotted. Cool. Oh, that's triggering. So I'll make that dotted, and then you just draw your hyperbola kind of inside that, if that makes sense. So I know that because this is all positive, I'm going to end up in this quadrant and this quadrant. So you just draw it so you're avoiding your asymptotes. So I'm going to draw there and there. Now, once you've drawn that, it should be quite obvious that you have an x-intercept here. That's something you can find, and that's not that bad. So if I go, I want my x-intercept. Now, I know it's going to be a negative value, so you kind of know what you're looking for already. So to find your x-intercept, what do? Well, you make y equals 0. So thing is y equals 2 on x plus 1. That means 0 equals 2 on x plus 1. That means minus 1 equals 2 on x. So like the trig, you make a little, actually I'll just multiply it up. Minus x equals 2, x equals minus 2. So that means that point there is minus 2. So minus 2, 0. That's my y-intercept. And then I don't really need to have a point here because I've got my point now. So that's that. Cool. So same thing with this other one. The only difference is instead of moving up and down, so there could be a plus c, and there's not, it's inside or right next to my x. So I'm moving it to the right too. So again, I just think about where my asymptotes are, like in my head. This isn't being moved up and down, so I know it's going to stay there. It's this one that's going to move, the left and right one. So I'm going to draw one here. Now I'm going to move it, so this tells me I'm going to move it to the right 2. So I'm going to grab this and I'm going to go 1, 2. I'm going to rub out part of it, so it's actually dotted. Is that good enough? Hope. Okay, so that's my asymptote, probably too high. And then I just draw my hyperbola where, like avoiding the asymptote. Now, this minus, so that minus tells me it's in the second and fourth quadrants. So it's the opposite of what I had before. That means I'm going to be in here and here. And I just draw my hyperbola like I would before. Like that, and like that. Now again, I don't have any sense of scale, but as soon as you move your asymptote, hold this right there. As soon as you move your asymptote, you're going to have an intercept. See how before I like the 1 on x, I didn't have an asymptote at all. Now I actually do, so you might as well just chuck it in. This point is going to be, now it's my y-intercept, so the y-intercept, which is going to make x equals 0. So that just means y equals, I'm just literally looking up here, y equals minus 3 on 0 minus 2. So that's going to be 3 on 2. So that's the point 0, 3 on 2. And that's fine. That's it. So all we're really doing is moving hyperbolas up, down, left, right. And as per tradition, let's chuck this in. And I'm going to make this a little bit different. Let's go like this. 3 plus y equals 4 on x plus 1. And give me x and y intercepts. I think I put extension in this one anyway, but I guess that's just a fun little challenge. So again, in year 10, we don't go much further than just moving up, down, left, right, like separately, but you just need to recognize that obviously we can do everything we've been doing before. Yeah. Okay, I guess that's it. 15 minutes, that's not too bad.